Okay, so welcome back for the next installment. So we started briefly on promise CSPs last time. So we will continue with some more examples and also some how you can extend this polymorphic theory to promise CSPs. Okay, so very briefly, what was promise CSP? You had two set of templates, some relations, and then lambda maybe, or let's call, I think I called it maybe A and B. So this is probably a little bit easier I can remember. And then there exists some homomorphism from D to E, or just a map such that phi pi is subset of qi for all I. Okay, and the point is you give me some CSPA instance, and now I'm happy if you only satisfy it using the QIs. So the promise problem is that given some instance, is it satisfiable as a CSPA instance or not even satisfiable as a CSPB instance? Okay, so we saw some, so now let's continue with some more examples of this. So basically to give an example, I just need to give these predicates. We already saw this T out of K sat problem. So here, here you allow negation. So there is one relation 0 1, which 0 1 1 0 in both, which allows negations. And otherwise, there's a single P which says at least T out of K are 1, and in Q you say that at least 1 out of the K are 1. Okay, so this is the promise version of SAT, very natural problem. So we saw that last time. We also allowed things like exactly J for 1 less or equal to J less or equal to K minus 1. So this was A. Right, and then B, again, I'm writing it a little bit more colloquially. Last time I wrote it formally, but this is the same example. And Q is basically not all equal. Every one of these is not all equal. Because, of course, note that the number of these relations should match because they're indexed by the same set. So here the idea is that I give you can think of it as actually some sort of hypergraph coloring problem. So, and it's actually, you can actually allow the K to vary as well, but let me think of the K uniform K. So you have some hyper edges. And basically each hyperedge E in E comes with some number B sub E, which belongs to 1 to K minus 1. And being satisfiable according to CSPA means that there is a true coloring where exactly B sub E vertices in edge E get red color. So given that promise, and since B sub E is not 0 or K, this in particular is a valid true coloring. So I'm promising you a very structured true coloring. And then Q, this B just says that you should true color it so that not all the things are equal. So you don't care exactly how many are red in an edge as long as not all are red or all are blue. Okay, so that's the true coloring problem. And so this is another promise CSP. And we actually said that this was in P. And we said that this is in P if and only if T is at least K over 2. Okay, so these are already examples where we know what the answer is. Okay, so we can also do another example. So A can just be one relation. A can be this relation which is it's a symmetric relation. So you could say that J, or let's say T or T plus 1 once. Actually, let me just write it this way. This is too colloquial. So A is one. Let's say P discrepancy 1. So what I mean by this is it's basically all those strings in 0 1 to the 2T plus 1 for which the number of x's ones in x is it's roughly balanced. Okay, so the number of ones in x is T or T plus 1. And then that is this, and then B still is not all equal. So this is just one relation, and then note that this is a smaller relation than this. And what am I saying here? So I give you some hypergraph again, which is 2T plus 1 uniform, and it has a true coloring which is almost perfectly balanced. Okay, it is almost equal number of zeros and ones in every hyperedge, and then you just have to true color it. Okay, and so you can make this for 2T plus 1 balanced, and then you can also define a version for 2T where it's exactly balanced. Okay, so let's just do that as well. So A is exactly T out of 2T, and B is not all equal. Of course, this is a simpler problem than this in some sense. This is also in P, but this is NP harder. So given a hypergraph which has a very good discrepancy, so discrepancy is defined as the difference between the number of reds and number of blues in the worst, most miscolored or skewedly colored hyperedge. And so that's a discrepancy 1. And even if I give you a discrepancy 1 hypergraph, you cannot true color it. Okay, this is also NP hard. I mean, these things require proof. So these were in these papers in this paper with Austrian and Hostad I mentioned before, which was, first started studying these promised CSPs more formally. All right, let's do some more examples maybe. It's good to see several examples. And I already started with the 3 coloring versus 5 coloring. Let me do one more example to show something which can be that the domains D and E can be different. So far everything I said, the domains were, well, for coloring I guess it was different, 3 and 5 and so on. But let's see one more example. So this is K-partite. Again, I'm writing it very sloppily, but I'll explain what it is, and B is 2 colorable. So what do I mean by this? So A is going to have just one relation. So this is another example. So this relation P will be basically all those things, X in K to the K, such that it is a permutation. This is notation clear. Basically, it's a K tuple where nothing repeats and everything occurs exactly once. Okay, so it's got K factorial out of the K to the K possibilities. And that's K-partite, because now you can think of this as having a K uniform hypergraph, and then the value tells you which part you are in, and you're basically stipulating, saying that P of some tuple is true means that these K vertices constrained by that hyperedge are in K different parts. So this is basically K-partite hypergraph. Okay, if you take K equals 2, this is just bipartite graph. And what will the relation in each of these will have just one relation. This is the relation K-partite. What is 2 colorable? It's the same thing, not all equal, of arity K. Okay, and once again, it's pretty clear this is a promised CSP, because if you are satisfiable this way, what you can do is you can take the first K by 2 colors and call it one part, and then remaining as the other part, and that will be a valid 2 color, right? Because so if you're satisfiable according to this, you know that you can put the vertices, let's say K is 4, you can put the vertices in 4 parts such that every hyperedge goes like this. But then you can make a Boolean cut by just taking the first 2 things and calling it 0, the next 2 things and calling it 1, and that will be a valid 2 coloring. Okay, in fact, it will be even more than a valid 2 coloring. It will be low discrepancy. I can even put low discrepancy here, and that will be also valid. Okay? And why is, and formally, of course, this is not a, so the map here would be that phi from K to 0, 1 will simply be like whether you're 0 or not. So phi of A is indicator of A greater than K by 2, let's say. Okay, that's a map phi, and clearly that maps P inside Q. Okay, so. And this is actually also in P. Okay, and this is a nice algorithm. So we are 2 methods. So I won't tell you what the algorithm is, but actually I can tell you what the algorithm is, but I don't want to analyze it. So one is based on random walk, another is based on STPs. Okay, both algorithms work. So what's the random walk algorithm? You basically okay, so the random walk algorithm is, okay, so essentially you basically do a random walk, you find some sort of partial coloring, and then if there is something which is monochromatic, you just flip a random thing in that thing and keep going, and you just analyze this. So the random walk algorithm is simply take some arbitrary true coloring, and if there is a monochromatic thing, you flip a random thing and keep going. Okay, and you have to analyze it carefully in this context. The SDP one is a little bit much simpler. You basically have a vector. I mean, if this won't make sense if you haven't seen maybe these algorithms before, but it's very simple. For each vector vertex, you have to give one of K possibilities. So instead of giving 1 to K, you have K vectors which are form the simplex, K simplex, which add up to 0.
And the random walk, how does K influence the running time?
How does K influence the running time? Yeah, actually the analysis, you only use the fact that there are 2 colors such that in every hyper edge, those colors are exactly equal, and you just track it in that. So K shouldn't come too much into the analysis, I think. Intuitively, as K becomes larger, you're getting more and more information, but the random walk algorithm only uses this. So this algorithm is in a paper of McDermott, or it follows from that. Yeah. So note that if K is even, there is a simple algorithm, because you could say there's a discrepancy, 0 coloring. So then you could just forget the fact that it is K part, right, and just say that it's got a coloring where there's equal number of reds and blues, and then you can do exactly, analysis as if it's a balanced colorable hypergraph, which I said is in P. Okay, then there are also other algorithms based on linear equations and so on. But here, when K is odd, you need a slightly more, it's more or less the same thing. And the semi-definite program is that for each vector, each variable x, you have these variables x sub v1 vectors, x sub vk, so these are vectors, and these form, you can insist that they form a simplex, so they add up to, you will have these many vectors, and these vectors supposed to add up to 0, but now if you have some hyper edge involving u, v, w, x, right, or z, you basically say that the sum of the these vectors is equal to 0, and then you do random hyperplane counting. Okay, I'm not explaining it very clearly. Let me just see if I can do justice in a short time. Let me just skip that, and then if there is a fairly simple algorithm which will do this. Okay, so, but then you can replace this q by something else. If I replace q by discrepancy 1, which is also satisfiable by this.
So the vectors are n dimensional.
The vectors will be in n dimensions. Yes. Yeah.
So the vectors somehow have to be rounded to give you the 2 colors, is it?
No. So sorry, I think that I didn't. Okay, let me just say this properly. So for each v, there is just one vector xv. Okay. So this is the. Let me just. So this will be in some Rn. Then is the number of vertices, and the constraint will be that if you have a hyper edge v1 to vk, is an edge, you'll simply say the sum of those vectors is 0. This is the constraint you can put, which you can just say that the norm square is 0. And those are all the constraints, and you try to find vectors.
Or you want a hyperplane that puts some as negative and some as positive.
And why is this feasible, first of all? Because for each vector, depending on its value, you can give one of the vectors corresponding to the k simplex. And then if the k things are distinct, then they will add up to 0. So this is a feasible program. Okay? And how do you round it? You just take a random hyperplane, and okay, there's a pathological chance it's orthogonal to all of these things. It will not happen, right? And then it must have positive dot product with one of these and negative with the other, and that's your 2 color. Okay, so that's really the program. So you have one vector for each of these, and for each hyper edge, you just say that the vectors cancel out. Okay, but it's a very fragile algorithm, because so here I said that not all will be equal, but I can even relax it slightly and say, can I get a balanced coloring? And such things are not known to be in polynomial time, because this might, still the dot products may be such that k minus 1 are positive and 1 is negative. If you now ask, can you get k minus 2 to be positive, and can you make sure that it's not all but one is in one color and the other one is not? That's not known to be in polynomial time. Okay, so there are very basic things we don't know, but this one is. So let me just erase that so it's not confusing. But anyway, this problem is in P. Okay, and the main reason I showed this is that there's you can change domains and still get interesting problems. And let me also talk about promise graph, promise homomorphism, PHOM. Right, so what is this PHOM H1, H2 problem? So you're given 2 graphs, H1 and H2, such that there exists a homomorphism from H1 to H2. So I give you 2 such graphs. And then the question is input a graph G. So you have to distinguish between S and the no cases. Yes case, there exists phi from G to H1. And no, there does not even exist a homomorphism from G to H2. So this is again a promise CSP. It's a specific form of, this is exactly like the digraph thing, and here I'm even thinking of these as undirected graphs. Undirected. And note that the approximate coloring problem is false in this. So the PHOM K3 versus KC corresponds to the C coloring problem. Of 3 colorable graphs. Okay, this K3 being 3 click, so and this is C click. Let's say C is 5. So this captures the graph coloring problem. But it also captures many other interesting problems. For example, I can have PHOM C the 101 cycle and K3. Suppose I give you a graph which has a homomorphism into a very big odd cycle. Note that an odd cycle has a homomorphism to K3. So given such a graph, can you at least 3 color it? Okay. So we don't know the complexity of these problems. These are all open. Okay. So I will make a bold conjecture that PHOM, so this is again undirected graphs, H1, H2 is in P if and only if either H1 or H2 is bipartite. Note that if either of these graphs is bipartite, it's an easy problem, because this, again, this is something I should have commented perhaps. If I have a PCSP A comma B problem for a pair of relation things, if either CSP A is easy or CSP B is easy, the problem is clearly easy. It's only interesting when both A and B individually are hard, but somehow, and then there's a sensible new question to ask. Okay, why is that? Because if I have to tell if it's satisfiable according to A or not satisfiable according to B, if either of those is something I can check, then I'm done. Okay, so it's only interesting when both the CSP problems are hard. So if either H1 or H2 is bipartite, we know that the homomorphism problem is just checking bipartiteness. So that's easy. And every other case, the CSP is hard. That's known by the Hell-Nash-Ritterl theorem. But what about if I take a pair of graphs, one of which is homomorphic to the other, and ask this promise problem? So we know very few cases where we know this to be NP hard, proven to be NP hard. I would conjecture that basically every other case other than the trivial one is NP hard. So in particular, knowing that a homomorphism into a big odd cycle shouldn't help you 3 color a graph. Okay, or even like you can even put K100 here now. That should also be hard. So really, and this is like almost a bipartite graph, right? It's having a big isomorphic to a large odd cycle is almost like a bipartite graph, and that still doesn't help you to color it even with a million colors. Is conjecture I would make, but could very well be false. But there's a lot of things we don't know about promised CSPs. All right, so I think that's good number of examples. Are there any questions about the formalism or anything? No? Okay. So,
Sorry, is anything now? H1 and H2 are very different from each other. Like somehow this PHOM C101 K3 would be easier than something like K3, K4, K3, K5.
yeah, it could be easier, but I would, maybe they're all hard. But yeah, actually what will be very interesting is if you disprove this conjecture, even taking 2 graphs which are wildly different. And in some sense, it's also not, it's actually not, the question is basically just PHOM, maybe I'll make this comment. It's basically just CK, or let's say CT, KT or something.
Okay. Now what I meant was,
Because this is the most, if you're thinking of graphs which are as different as possible, so clearly, you can replace the host graph H2 by a clique on that thing. And because H1 is not bipartite, it's going to have some odd cycle. So basically, you can say that for any pair of integers, R and S, CR, KS problem is hard. And that's like the most separated thing. So that's it. So the question really is that, if I tell you have a homomorphism to a huge odd cycle, does that help you to color it with some constant number of colors?
What I had in mind was, so suppose H1, H2, H3 are 3 graphs,
Mm-hmm.
and there's a homomorphism from H1 to H2, and there's one from H2 to H3. Then P form of H1, H2 should be harder than P form of H1, H3. Is that, in the sense that
Right,
H1,
yeah.
H3 will reduce.
Yes. That's formally true, right?
That is
But
clear.
yeah, that's clearly true. Yeah.
So in that sense, under homomorphisms, you have a partial order on graphs.
Yeah.
Things that are kind of more apart in that partial order.
Yeah. And that's more or less what I'm saying here. So the point is, basically what I'm saying here is that if I have any H1, H2 which has a homomorphism, so this will have a homomorphism to some KT. If this T is the number of vertices here, let's say, some crude upper bound, and basically the chromatic number of this. And this side, it must have an odd cycle. So there is some CR. It contains an odd cycle because it's not bipartite. So it must have this. So these are the two extremes. So if you want to give an algorithm, this is what you need to do, or disprove the conjecture, that's what you do. Or if you want to, you just prove it for this, you have proven the whole conjecture. So it's really just sort of one kind. It's basically a question of coloring graphs which have a homomorphism into large odd cycles, which we don't know much about here. So it could be interesting to study. Even given such a graph, can you color it with, say, log n colors? It wouldn't do anything to this conjecture, but it will still be interesting. It will be much better than what is known for 3 colorable graphs or anything. Yeah, so I like somehow this promised CSP raises many interesting new questions, which is very easy to state, and we seem to know very little about them. Okay, so now I want to talk about polymorphisms. So now, so all this is fine. So we have this many examples. Some of them fall in P. Many of them are NP hard, and many cases we simply don't know the answer. Okay, and so that's the difference from CSPs, where we had the dichotomy. Here, it's not clear if there is even a dichotomy, and even if there is a dichotomy, we are very far from establishing it or even conjecturing what a criterion should be. Okay, so that's the thing. So let's now talk about polymorphisms in this case. It's going to be a very natural generalization of what we saw before. So how will you do polymorphisms here? So first, so you're going to have a pair of relations. Okay, P and Q, and then we'll generalize it to. So once I define it for a pair of relations, one of which contains the other, or phi of P is contained in Q, we'll extend it to this by just taking the intersection for all Pi, Qi inside this. Okay, so this will be just defined as intersection over all I of poly Pi, Qi. If A consists of Pi's and B's consists of Qi. So we just have to define it for one relation. And we'll basically generalize, in the case Q equals P, obviously we want to go back to old polymorphism. So what was the case? So we just said that if I had some n tuples, so x2 in P, so xl in P, or let's use m. So you had a function f d to the m to e. Okay, here I'm changing the domain because Q could live in a different domain, but the polymorphism is from d to the m to e. If you take any m tuples in P, apply f column wise, so we just define that to be, by abuse of notation, that must be in Q. Okay, for all this must be in Q. So it's really the same thing. You write down tuples. Let's say arity is 4. You apply f column wise. You're going to get another tuple. And earlier you said that if these are all in P, you must get an output in P as well. But now you don't. You're okay if the output doesn't quite lie in P, but it lies in Q. That's the condition. And once again, there are non-trivial, it is not an empty definition because you can take the dictator functions. And I guess in this case, you will apply phi to it. So if you want to change the map. So now there is also a map phi from D to E. If this bothers you, just think of D equals E and forget about phi, just identity. Okay. So again, they have these projection functions. So those are always there. But this is for any pair of relations, you can define this. And for any pair of sets of relations, you can define it like this. And
so if you take any polymorphism of P, you can compose it with phi, that will be one set.
Yes, yeah. But the point is exactly, so you could just, so if P itself had some polymorphisms, you could just apply that. So in the case P is contained in Q, you can stop there. But if you are in this more general setup, you just apply phi to it. So phi composed with any polymorphism is a weak so this we called something called weak polymorphisms first. In our papers they're called weak polymorphisms. But these algebraists sort of objected. They said there's nothing weak about it. So we are trying to sort of pull back on our terminology a little bit. So because we want to draw their attention and get them to work on these, we'll name things like, that's the least we can do, is name it so they're happy. So they said this should be just polymorphism in there's nothing weak about it, so it's just for pairs of relations. And I should also mention that this sort of notion was really studied by Pippenger back in O2 already in some other context. So he had some reason to study pairs of relations, and he studied these kinds of objects. So it's not entirely, it's not entirely new, and it's a very natural notion once it's sort of a failure. The first thing which will come to mind when you try to extend. Okay, so it's not surprising, and it has come up in previous works as well. Oh, I shouldn't have, never mind. So now I was just going to list the polymorphisms for each one of these things, but I just erased it, but that's okay. But maybe first I'll tell you what's the use of these things. So we have this Galois connection, which we saw before. So which we said that if polymorphism of P or A is contained in polymorphism of B, I'll just do the reduction type direction, then CSPB is easier. CSPA. Okay, it was log space, let's just say polynomial time. So in some sense, having more polymorphisms meant you're easy. Okay. So we can now generalize this to the land of promised CSPs. So what Josh and I, once we observed these things, we just went over this proof, and really it's a syntactic change. So let me write down this connection. So if polymorphism of AB is contained in polymorphism of CD, that implies the PCSP C comma D is reduces to PCSP of A comma. All right? This is something we can prove. Okay, and proof just by similar to before. So let me just say one word about it. So earlier we had this relation, you might remember this S sub L relation, so for the hard direction, I think one direction is pretty easy if you do reduce. Okay, so the other direction I have not stated, but if you say that there is sort of a simple reduction, you can generalize this PP reductions also to promised problems, basically these gadget reductions. So if you have a gadget reduction from PCSP-CD to PCSP-AB, the fact that the polymorphisms are all preserved is something proved by inspection. The harder direction is to really prove this. So if you have more polymorphisms, then you do indeed reduce. And for that we use this intermediate relation, right? So and that intermediate relation was based on polymorphism. So we basically said this was F in F from D to the L to D, such that F was in polymorphism of A, I guess. Right?
So the elements are these huge.
Yeah, huge vectors. And now so I don't want to go back to that proof, but basically we just have to replace it by a pair of relations. In the one case we will keep the polymorphisms. In the other case we will replace it by the polymorphism of A comma B, the weak polymorphisms. That's what we'll do. And the proof will just go through. Okay? So it's the same thing we'll do. So if you have more polymorphisms, you can reduce via these intermediate things. Okay. So here now you'll replace it by two things, S prime L and T prime L. This will be the same thing. F is in poly AB, which you can write as poly A comma A. And in the weaker relation, you will only ask it to be a weak polymorphism. Okay. And then that's the gadget you use in the reduction. That's the tool you use in the reduction. Okay, so in any case, if you have more weak polymorphisms, you are reducible to the other problem. And this is good again because this says that up to polynomial time reductions and equivalence, this is a fine enough tool. So if two things are interreducible to each other in particular, they must have the same polymorphisms. So the weak polymorphisms or polymorphisms of a pair of relations has adequate information to go about trying to classify the complexity of these things. And indeed in all the cases we have algorithms. Okay, so with that actually what is going to be the philosophy? Okay, so now you can imagine making a dichotomy conjecture or something like that. So now a rule of thumb for the research program so far, and it's still in infancy because we don't know what the formal statement is that so rich enough Pol AB. So if you have rich enough weak polymorphisms implies algorithms. And let's say paucity or rich enough or interesting, paucity of interesting polymorphisms in this relation tends to be hardness. Okay, but unlike the CSP case where there was a very clear definition of what this rich enough or interesting was, and they exactly matched, so you either in one case or the other, here we don't quite have an idea what even the definition should be. So what we have so far is lots of several results which give evidence to this sort of a thesis. Okay, you can now think of this as some polymorphic principles. Somehow polymorphisms beget algorithms even in the promised CSP world. So if there are interesting ways to combine solutions of P to form a solution of Q, many rich ways, then you tend to get algorithms. And if there is some severe lack of such polymorphisms, the only things are not very interesting, basically like projections or juntas or something, then we get hardness. So we have results of this form, but they're, they don't match, and we don't even have a conjectured criteria for what the boundary is. In fact, it's not even clear to me that there should even be a dichotomy in this case, because the set of problems is so rich now that there might very well, you could imagine having some Ladner type theorem creeping in. So we just don't know, which will also be very interesting. So what I want to do now is go over some examples of weak polymorphisms. But one thing you might say is, okay, why is this the case? Why is the theory, it seems like so far the definition is very natural. It seems very clean. Why doesn't the theory just extend? Okay, and the main reason is something you might already sort of appreciate from the definition, is that what is one crucial properties of polymorphism? So we said that, for example, if you had majority 3, then I can compose it many times, do some minor or projections to get any majority. So here the key flaw, the trouble with, so here let me say weak poly. So this is sort of why I think the weak polymorphism name is not too far off, is that they do not compose. Or they are not closed under composition. Let me be more precisely, not closed under composition. Okay, so what was composition earlier? We said that you could take an arbitrary tree, whatever you want, and the leaves you could fill it with any values, indeterminates with repetition in any order and all that, and then you just have to label these things with different polymorphisms, F, G, H, F, and so on of the correct arity. And then that will be also a polymorphism. And that was simply because whatever things you fed, the output was also in the same relation, so you could keep going. But here the problem is, even after one application, the output is not in P, but it's in Q. So then we don't know what to, so we can't compose again. So you can't even do f of something, comma f of something. Let's say it's arity 2 things, so you can't do this.
It's the same thing as saying that you can't write every polymorphism from P to Q as a product of a polymorphism, composition of a polymorphism.
Yes, there are other interesting ones. That's right. So indeed, because I'm going to, as I said, this whole theory is only interesting when CSP A and B are themselves hard. And we know that in the CSP case, if they're hard, there are not many interesting polymorphisms. So if every weak polymorphism came as a composition of an honest polymorphism followed by this embedding, which in the case when D equals E will just be identity, then the theory wouldn't have more weight. But the point is there are A and B which are individually hard, but for which there are interesting weak polymorphisms. And so you have to study them. Okay, so they can be much richer. So this is a big problem. Okay, but fortunately they still have some structure at least, so they are still closed under minors or projections. So what I mean by this is something again we saw before, a very special thing which follows from the fact that all the dictator functions are there and the compositions are there is the following thing. So if you have some map from L to R, okay, and so you have some polymorphism F from D to the R to D, I can define a new polymorphism F pi of F pi from D to the L to D by just simply saying F pi of X, X1 through XL, okay, it's just going to be X at pi of I. So did I do this right?
Pi is a projection.
Yeah, pi is just any map. No, I think I did it backwards. Sorry, projection closed. I wanted, so this one should be in L. So basically I'm just saying that if I have some big polymorphism, I can do substitutions like this, and then that will also be a polymorphism. Okay, so I just got it backward, I think. So this should be from R to this. So F pi of X1 through XR, right, is simply X, F of X pi 1 to pi L. Okay, so if I have a big polymorphism, basically I can identify any subsets of variables in any way I want. I can shrink the arity of that polymorphism. That is still, so if you have a big arity polymorphism, you can also do this. That will also be a polymorphism. And why is that? That's simply because you can just repeat, you're allowed to repeat entries in an arbitrary way you want. Suppose you have to give me an L tuple, it doesn't have to be a tuple of distinct elements from the relation. So I can just repeat things whichever way I want, and that can, therefore I can form a smaller arity thing. So I can always do, so it's always, so this is basically, it's still closed under projection. So we call this projection closed. So this is some foothold we have. So if I have some big arity thing, that will also imply some small arity things. But this is more or less the only structure we have. So PCSPs are very rich. Poly AB can be very rich. So essentially any family of functions which is projection closed and something called finitizable is any projection closed, which is exactly this property I said, plus finitizable family of functions is equal to poly AB for some AB. All right. So the only thing I didn't define here is what is finitizable. Finitizable simply means that if f is in, so there is some finite arity, so there is some arity R such that f is a polymorphism, is in the family, is in this family. So any projection closed finitizable family f, I'm claiming is a weak polymorphism. Finitizable just means that there is some finite point which depends only on these a and b, such that if you take any function, it will be in the polymorphism if and only if there is some projection of it which lies inside the arity R function. Okay, if and only if is in f, if and only if there exists some pi from L to R such that f pi, which is now an arity R function, is in f. So somehow there is some arity at which if you tell me all the arity are functions, that's enough to kind of describe all the other things. But it still feels like a more combinatorial or topological type property than an algebraic one, because there is no closure under composition. So you could take R to be some million and write down some crazy sets of functions of arity million, and then just say, well, close it under projections, and then there will be some A and B for which that's a weak polymorphism. Okay, so this somehow says it's really a very rich family. So a set of polymorphisms can arise is very rich, so you're not going to be able to sort of tame it into few classes like the algebraic thing said, because the whole point about algebraic thing was it was some sort of a dichotomy at the algebraic or structural level. Either you are very simple, essentially just projections, or you are extremely structured. Somehow there was no in-between ground because of this closure under composition. And that somehow manifests itself in the complexity world as well. So either you are hard or you have an algorithm. But here all these intermediate rich things are possible, so it's not clear what you can do. Okay. So one other fact because of this is that if you have one element in this thing, you can't. Earlier I said that for polymorphisms, if you have majority 3, you're easy because you can just compose things by itself and so on. But I can actually give you promised CSPs which has majority 3 as a weak polymorphism, but it's still hard. So somehow having one or a small number of weak polymorphisms does not mean anything. You really need something like an infinite sequence of structured polymorphisms to get algorithms. Okay. And so it's not clear, therefore, exactly what the boundary between easy and hard is, if at all there is a boundary, and what is exactly the delineating point of what gives algorithms and what lack of which gives hardness. Okay, so that's the theory. Okay, so this is still sort of general facts. So now what I'll do is, now let's see some examples of promised CS. The polymorphisms corresponding to many of the relations we saw. Okay, so all right, so let's do one example. So P was basically all those things in 0, 1 to the 2t plus 1. Yeah, exactly, Hamming weight K, let's say, T. Plus, and then you also have plus negations. So allow negations. This is the basically I'm doing the T out of 2t plus 1 sat prop. And then Q is basically all but the all zero string. Okay? So this, as I said, is NP hard. But still it has some weak polymorphisms. So you can check that majority of arity 2t minus 1, of arity 2t minus 1 belongs to polymorphism of this A and B. Okay, this is also plus 0, 1. So this extra relation just enforces negations, as I said before. Okay, because without that, of course, this problem is easy. You can just set everybody to 1, right? So majority of arity 2t minus 1 is polymorphism in the poly. For example, for 2 out of 5 sat, which is the t equals 2 case, you have majority of 3 things is a weak polymorphism. Okay, and this is something again we could probably see by just example. So you have 5 sat, right? So 1, 2, 3, 4, 5, and you have 3 things. And you know that in every row there is at least 2 ones, if each of these are in P, which means there are a total of 6 ones across 5 columns. So some column must have 2 ones. So if you apply majority, you will get a 1 somewhere, and that will belong to Q. Okay, very similar to the argument we saw before. So majority of 3 is a weak polymorphism, but you can check majority of 5 is not. In fact, one can prove that the only weak polymorphisms are like juntas, which depend on like 2t minus 1 things. So it does have some small corner cases. There are some simple cases, but it's not a very rich family. It's finite. It dies down quickly, and then this problem is hard. Okay, problem. So majority of, for example, majority of 2t plus 1 is not a weak poly. Okay, so that's something you can check by just giving some examples. Probably it's just some simple example like this will work. You just distribute the one sort of evenly as possible. Yeah, and then, so each column you can make sure has only 2 ones, and then you're dead. Okay, and indeed this is hard. So this is, so in fact this is not a weak polymorphism. In fact, every weak polymorphism is a 2t minus 1 junta. So what do I mean by junta is it's a function, the arity can be very big, but fundamentally the function only depends on 2t minus 1 or 3 things if t equals 2. So it's like, so you have functions which are a little bit richer than projections, which only depend on, which are dictators depending on one coordinate, but they don't depend on too many coordinates. Okay, and this belies NP hardness. So you can prove belies NP hardness. Okay, so if you can indeed for any promised CSP, if the only weak polymorphisms are some juntas, then you can crank through standard label cover hardness machinery and prove that this PCSP is NP hard. So that's not a problem. Okay, but all right. So now let's in this theme. So let's do one more case, 2. So let's just change this to t plus 1, or let's just change it to t out of 2t sat. So I just reduce this arity by 1. So it's the same problem, but now, the strings live in length 2t. So now you can actually prove that majority of L for all odd L is in poly A, B. So now if you have 2 out of 4 sat or 5 out of 10 sat, then any odd majority will work. And the proof is again the same thing. You just write any L tuples. Okay. In every row, there are at least t ones. So the total number of ones in this whole configuration is at least L times t. Okay. So which means there must be a column. There are only t columns on the other hand. No, the number of 1 should be L times.
There are 2t columns.
There are 2t columns, and each has t ones at least. So there are a total of LT things.
So
There's
there's a column with L by 2.
a column with at least L by 2 because there are 2t columns. That's right. So that's the part I missed. Thanks. So there must be a column with at least LT by 2t, which is L over 2 once, and L is odd, so that you can take a ceiling, right? So you can take this once in some column. Okay, and therefore any odd majority works. And note that t equals 1. This is just 2 sat. So this is just a sort of a promise. This is a more general philosophy, and why 2 sat is easy. Okay, for 2 sat we said all odd majorities are a polymorphism. Really the same thing is going on here. So again, and this is indeed in P. So this problem is in polynomial time. So already here it's a very special case, but it shows this thing. So if you have paucity of polymorphisms, you get hardness. If you have rich enough polymorphisms, you get algorithms. But of course these are special cases of what is lack of enough rich polymorphisms. If the only ones are junta, you get hardness. If you have all odd majorities, that's a very nice class, then you get algorithms. Okay. So you have to try to develop more theory to understand more things. So what I might do today is I'll probably describe an algorithm which it doesn't care if it's a CSP or promised CSP, which works if there are all odd majorities. Okay, so I'll describe that algorithm shortly, but let's just see some more examples and some more interesting things.
What does that algorithm look like, say, for at least 2 out of 4 of the promise version?
So there are two algorithms. So for T out of 2 sat, you can again do this random walk algorithm. You could start with an arbitrary assignment, and if there is a falsified clause, you just flip a random one. And the idea being that you will move to this balanced assignment towards it with probability half and away from it with probability half, so it will be an unbiased walk. That's one algorithm. I don't know quite how that relates to polymorphism. The other algorithm which I'm going to describe is linear programming based.
So that is deterministic.
That's deterministic. So there's an LP based algorithm which only, it's a generic, it's actually in the same spirit as what we saw before for Hornsat and this. You just write the LP down and you just give a rounding algorithm. Okay, so that's what I want to say. But let's do one more, let's go back to some examples. So many of the other examples I gave were hard, so they're not going to have rich enough polymorphisms. But one of the examples was easy, which you might remember was A was all this exactly J, for J not in the boundary, and B was all not all equals. So this was a case where we said there was an algorithm. Right? So remember this is the hypergraph problem I started with. So these relations are stricter than this because here I tell you exactly how many ones I'm going to have, and here I only stipulate that not all of them are ones or all of them are zeros. So this is a nice promised CSP, and we said this is in P. So what are the weak polymorphisms for this? So we'll actually work with just one of them. Suppose, let's say P sub A and not all equal. So let's just consider one of these things where A is just any value. And I'll give you some nice polymorphisms for regardless of A. So then of course when you intersect it for all A, that will also be there. Okay, so let's try to consider what this is. I don't know, so I'll give you nice functions in this. So any guesses for what? So again, let's try to maybe discover it. So you have K things here. And what do we want? Let's just see what the property should be. So if I have ones, A ones anywhere, that's a valid thing in P sub A. So suppose I write L of these. Somehow we use L because L is the number of labels in label cover. But otherwise it's a very strange thing to use capital L for the arity. Okay. So if that sort of bothers you, just change it to M. So M is going to be the arity. So the point is exactly A ones in each row. And now we need to output something at least 1, 1, at least 1, 0. So whatever thing you output, don't care. As long as you see a 1 somewhere and you see a 0 somewhere, you're happy. And no matter what tuples you write, this function should have this property. Okay. Okay. Want to think about it, or shall I give away the answer? Maybe actually I want you to think about it because maybe you'll give me one I don't know. And note that there may not be a unique one because you are projection closed, right? So you can even do other things. And actually maybe you want to think about the case when you have just, let's say, 3. Just 3 of them. Think of M as 3. So I don't know if it necessarily makes it easier, but okay, let me give you a sort of hint, or let's try to discover it. Before, the nice thing about this is that in every row, you have exactly A1s. So if I simply sum up, so if I sum this row up and subtract this row up, I'm going to cancel out exactly. So that's what my polymorphism will try to do. It will keep adding the odd rows and let's say subtracting the even rows. And now the point is all the odds and evens will just cancel out. So for example, if you do M is 3, and if I take my f of x1, x2, x3, think of just doing x1 minus x2 plus x3. Of course, this is not a Boolean function, so it's not well defined, but let's just see what this would be. The point is when I sum this up over all the different columns, I know my answer will be exactly A. Because all the top m minus 1 things will cancel out, and then the last one will give me an A. So when I sum up this f value, if I define f to be this function, and then sum it up over all the columns,
When m is odd,
when m is odd, yeah, m odd. When m is odd, that's why I said m is 3, so the sum will always be A. And that will, we didn't really use m is 3 here, but let's just write it down. So it's true for any odd m. So the sum of all the f's must be A. And A, remember, is more than, it's strictly between 0 and k. So in particular, not all of these things can be positive. We need a Boolean function, right? So not all of these things can be positive, and not all of these things can be negative. So we can simply say the indicator of this is at least 1, and that will be a valid polymorphism. Okay, let's go over it again, but this is going to be the polymorphism. And in general, this is true for any odd m. You take an alternating sum and take the alternating, so this is something we call the alternating threshold, AT, polymorphism. And this is actually the first non-symmetric polymorphism we are sort of seeing here. Note that the relation themselves are symmetric, but this polymorphism is not symmetric. It's sort of block symmetric. It treats odds and evens separately. Okay, and this is simply takes up, in general, it is 1 summation minus 1 to the I minus 1 xi, I going from 1 to m is at least 1. Okay, m being odd. And why is this a valid polymorphism? Let's just see again. If I sum up these values over all columns, I'm going to get A. So every column couldn't have been at least 1, because then the sum would be at least k, and A is less than k. So there must be somebody who's 0. On the other hand, not everybody can be 0, because if this Boolean function, if every one of these things is 0, then in every column you got a non-positive number. And then you couldn't sum up to a positive number, because A is strictly positive. That's it. Okay, if it didn't fully follow it online, it doesn't matter. There's not much to this argument. It just uses the fact that it's very important that in every row you have the same number of things. So this is a polymorphism for every such pair, P sub A and this, and of course it's also therefore going to be in the intersection, which is the definition of this. So you have lots of these polymorphisms. And that's also why you have an algorithm. Okay, so now I have about half an hour, so I want to spend, let's see if there is any general remarks I want to make, or maybe I'll, okay, so maybe I'll state a dichotomy theorem which we get, and just to, because we have all these polymorphisms in the board, and then I'll talk about the algorithmic results. Okay. So now I'll state, so even though I don't know if in general we have a dichotomy or not, I'm going to now state, well actually maybe I want to give some more examples. No, I think I didn't even state that PCSP. So let me skip that example and let's just go to this theorem. So if you look at both of these examples I've given, the relations P and Q are all symmetric. So namely, whether a tuple belongs to it only depends on its Hamming weight, not the exact ordering. Okay, so and that captures many of the natural things we talked about. So you can ask, okay, in general we don't know how to do this, but suppose all relations in A and B are symmetric, and then let's also assume you have negations. Okay, so this is basically allowing negations. Okay, so then consider PCSP AB. So if all the relations are symmetric in both A and B, plus you allow negations in both A and B, then you get an algorithm for PCSP AB in the following cases. So if you have all odd parities as a polymorphism, you'll get an algorithm. And in this case, basically what happens is that linear equations kind of are sandwiched between A and B. So then you get an algorithm. The other case is majority of M is in poly AB for all odd M. Then also you get an algorithm. And the third case, ATM is in poly. These cases you get an algorithm, else PCSP AB is NP hard. So this is some theorem we can. So if any of these conditions hold, then you get an algorithm. More than one might hold, you will still get an algorithm. But if none of the conditions hold, which means that you miss parity of M1, majority of M2, and AT of M3 for some odd M1, M2, M3, then you're NP complete. Okay, that's the dichotomy. So we have a clean dichotomy for Boolean symmetric PCSPs allowing negations. It's a slight inaccuracy here, but it's a very technical thing, is that you will also get algorithms if not these guys, but their anti-versions are. So you can take parity of M and flip it, and you can take anti-majority, and you can take anti-thing, and those will also be in polynomial. No, it's not covered by negations. That would be covered by setting constants. So if I allow to set any variable to 0 or 1, then you get something called idempotence, and then basically you can't do this flipping thing. Okay, so if I really say, if you do this and I allow you to set constants, which means the unary thing 0 and the unary 1 are in both A and B, then I don't need these anti things. Okay, but for simplicity I lied a little bit and just stated this. Okay, so star is that. Okay, so allow setting constants, setting to 0 or 1 as well. Okay, so this is something, that's a technicality. The negations is a more serious matter, but we need it for the theorem. So that's that. Okay. So a few words, and I guess the difficult part in this theorem is somehow the hardness, even though I think somehow conceptually it's not maybe the most interesting part, it's a lot of case analysis. So basically the structure of this thing is, so I'll just make some comments about this and then we'll move into the algorithmic part. Some comments. So the first of all, the algorithms don't need symmetry of relations. So if you give me any of these families of polymorphisms for a PCSP, I'll give you an algorithm. I don't need the relations to be symmetric or anything. Okay, so that's one thing. For hardness, we do crucially rely on symmetry because somehow symmetry really means that the relations are very simple. They're just defined by some subset of Hamming weights, and then we can really understand what majority and AT does to some subset of Hamming weights by just taking different rows with some different Hamming weights and one patterns in some clever way, and just lots of bare bones combinatorial analysis. So for hardness, basically we say hardness is based on the following sort of structural result: if parity M1, majority of M2, and AT M3 are all not in poly AB for some, so if you miss one of these things, then all F in the polymorphisms are sort of uninteresting in the following sense. So one uninteresting would be that we have already seen a couple of ways you could be uninteresting. You could just be a dictator, or you could be a junta. This will be a little bit weaker. So, or something called C fixing. So there is some constant C which only depends on A and B, for which you are C fixing. And what does C fixing mean? That means that suppose if I have fx1 to xm, there is some C coordinates here such that if I set them all to 0, my function, it's as if I set everybody to 0. Okay. And let's say you allow setting constants. So basically you'll just say that if f of x sum So, which means there exists some subset of coordinates in M, size of S is at most C, such that f of x, if x sub s is 0, then f of x is basically f of all zeros. So if there are some crucial coordinates, some 1,000 coordinates, if I set them all to 0, you might as well set everybody to 0. So in some sense, these coordinates have a lot of power on the value of the function, at least when you set all of them to 0. And this is enough to get hardness. You can interface this with hardness in standard ways. Okay. Basically, these small c coordinates have undue influence, so you're sort of Hunta-like. You're not quite Hunta. The reason I mentioned this is it's also not clear. We got Hunta. It would have been nice to say that that's the dividing line. If everybody is a Hunta, you get hardness. But it's not quite that. We can actually allow a little bit more structure, a little bit more richness, and still get hardness. So it's not quite clear what we can prove, and in terms of limitations of polymorphisms for hard things, and whether that is enough and so on.
So how crucial is that 0? Because if it's there's some setting to these bits, then you're just saying that there's a large monochromatic.
Yeah, that doesn't matter. We just get 0 in this case,
So
that's
you
all.
just want a large subgroup which is monochromatic in the function.
Yeah, for which some setting of those variables will.
Yeah, that's a subgroup.
Yeah, that's right. Yeah, I think that should be enough. I think. Yeah. So that's why we get hardness. Okay. So any weak polymorphism is C fixing. So you obviously any of the interesting things we said, like majority of large arity, won't be C fixing, because if you fix 1,000 coordinates, but my arity is a billion, these 1,000 coordinates don't matter. So in this sense, these are uninteresting, and this is enough to get hardness. Okay. So that's the second comment. Okay. Maybe the third comment I'll make, and then I'll move into algorithms, and not sure how much time I'll have, but I guess we can finish it up on Monday if people see that. So the third comment I'll make is, so what are the algorithms? So in the case of parity M, as you might imagine, it's just Gaussian elimination. Okay. And majority M, it's linear programming. Okay, and AT, you have actually a choice. You have two algorithms. You can still do linear programming, but the algorithm is, the answer is a little bit more complex, and but in some senses it's a good one because it generalizes in some other directions, because this AT is a non-symmetric polymorphism. So we can now ask algorithms for more general block symmetric polymorphisms. If you have, here you have just 2 blocks, but you could imagine 10 blocks, you're symmetric inside each and do something. So for those things also the LP thing will generalize, but you can also do our linear equations. Or say integers. And I already gave an example of this thing. So I had this simple thing of 1 in 3 versus not all equal 3. Right? Or in general, actually, for this, I gave you what the algorithm was. Basically, for each constraint, you just have each variable, you have an integer valued indeterminate x sub u. And for each constraint, you just say that the summation of those variables equals a, and solve it over integers, and then just do sign-based rounding. Okay, that was an algorithm. And that actually will work for any predicate, any CSP which has AT polymorphism. Somehow that's what was used. Okay, so I'll try to maybe discuss these algorithms. Any questions so far? Well, definition of ATM is it's just a function. So ATM of x1 through xm, it's an arity m function, is simply indicator of x1 minus x2 plus x3 plus xm, whether it's positive or not. So you sum up these things. If it's positive, you give, you say 1. If it's non-positive, you say 0. So it's like a signed threshold function. Okay, any other questions? All right, so let's try to see a little bit the algorithms. 2 algorithms, 10 minutes, so 5 minutes each. But it's enough to discuss 2 main tools. I think more than the algorithms, it's what kind of tools we use. So basically, those 2 algorithms come from one, which is the linear relaxation, or LP relaxation. And the other one is an affine relaxation. So these are both relaxations. So we have let's think about again Boolean case. PCSP or this thing doesn't really matter. So these algorithms, that's a nice thing, is that they really forget about the relations in some sense. The only structure of the polymorphisms matter. So these are polymorphisms for CSPs or PCSPs is not such an important detail. So we have this discrete Boolean problem. We want to relax it in ways which will allow us to solve the relaxation. Okay? And we already saw what this thing was. So remember, we saw this basic LP relaxation. Okay, again, I'll do it for Boolean. I think I described it actually for more general domains before, but now for each variable u, you can have some xu, which will just be in 0, 1. Okay, and for each constraint, and suppose I have some predicate on u1 to uk, right? Or let me use r because I'm using p for polynomial time a lot. So let's say, suppose you have some relation r. So you're given some PCSP AB, and let's take some relation r in A. Okay, so you have r constrained on this. So what we can have is that we can have a distribution on satisfying assignments to r. Okay, so you can basically say, so you can say alpha 1 to alpha size of r. Okay, so these are all positive, and then you say the summation of this alpha I is 1. So basically, you have a distribution. I'm just repeating what we said before. You have a distribution on satisfying assignments or members of R for each such R, and that can be given by these things. And now you also have xu, which is basically the marginal on this thing. So now you will simply say that xu1 is simply going to be equal to summation of all alpha I, such that let's say the relation, this guy is R1 through R size of R. So these are all the tuples in this relation. So you'll basically sum up all the alpha i's for which Ri projected to U1 at 1. No, and also that it's equal to 1. Yeah. So again, this is best seen as like, you suppose you have some 4 things, 0, 1. So you give some numbers to each one of these. Suppose there are 4 tuples. You give some numbers, 1/4, 1/5, something, something, which add up to 1. And now you basically just, if you have this distribution on the 4 tuples, that gives a marginal on each one of these columns. So you simply say that that marginal should be consistent with the marginal for each variable, which for the Boolean case is just given by one number, because you just tell me the probability it's 1 or 0. That's your consistency. Okay, so this is consistency, or marginal, consistency of margins. Okay, this is exactly the basic LP we saw before. So this is one relaxation we have. Okay, the other relaxation you can have, is this clear, the basic LP? So you basically just have a distribution on satisfying assignments, and then you have a distribution on values to each variable, and you just say that they are consistent. So this means that in some LP distributional sense, this is a satisfiable. So you just check for satisfiability of this. If this is not satisfiable, clearly your instance is not satisfiable. Why? Because you can, if there is a satisfying assignment, you can give each variable exactly that value, 0 or 1. And then for each relation in the tuple, you basically take its satisfying assignment. You put all the masks, you basically give point distributions, and they will all be consistent. So we are just relaxing it to aid solvability. But of course, you might be solvable in the LP sense and not solvable in the IP sense. That's what is going to happen. But the point is, if you are a majority, if you have majority polymorphisms for all these, this cannot happen. Okay. So that's one. So I'll state that, but let me do the, okay, or maybe I'll just state the theorem. So at least we. So here is a theorem. If majority M belongs to poly AB for all odd m, then LP satisfiability is equivalent to integers or Boolean satisfiability. Yeah, the polytope, so if the point is, yeah, so if it is satisfiable at all, then it must have an integral point as well.
But the vertices could,
Yeah, there could be other vertices, yes. Yeah. But I'll give you a rounding, so there is some subtlety here on whether it is a search version or decision version. Some of these things it matters, but here you can solve the search version itself. And so I won't, it's too much to call it a proof, but it's not difficult. It's really got more conceptual content than really anything technically difficult. So you basically write this LP and you get an answer. So the question is, how should you round? Somehow majority should be dictating the rounding in some under the hood somehow, and that's really related to thresholding, right? So you basically do the following rounding. So solve LP. Okay, so you get these values xu1 through xun for the variables. You forget about the constraints things. They exist, but they don't matter for the other thing. So for each u, set u to be 1 if xu is more than half, and 0 if xu is less than half. That's the rounding. So round. And then you can prove that this will be, so this will satisfy all constraints. Okay, so there's one thing very goofy about what I just said here, right? So there's some problem with what I said. Okay, this is not a fully defined rounding. So in particular, even you could just take your good old 2-sat, as I said, or even just checking bipartiteness. I can give you a graph and ask you if it's bipartite or not. You can make it, the LP will always be satisfiable, because for each edge you can put equal mass on 0, 1 and 1, 0 on the two ways it can be cut, and all marginals are uniform. So LP is satisfiable, but this one is not. So this is wrong. Okay, so, but a version of this is correct. So it's just that LP satisfiability, but if you never get, if you disallow half, then this is a true theorem. Okay, so what I'll do in 5 minutes is, let's just allow me to just assume that none of the variables are half. Then let's see that, then this rounding is well defined, and we'll actually just argue quickly that it's indeed sort of sound. It makes sense. And then we'll address this part. Okay. And why is this a good rounding scheme? And that's not, that's something, an argument which you have seen many times before. You have an arbitrary relation, you want to prove that that is going to be satisfied by this rounding. And somehow, therefore, you have to relate what this rounding does to each variable to what some polymorphism will do to that variable. So you have to do this map from this rounding to the polymorphism. In some sense, this rounding is some sort of a limit of what the polymorphisms do as m increases. Because somehow when you take majority of a very large thing, you're 1 when you're more than half and 0 otherwise. Okay, and this is like, this you're doing in the real numbers, but it's sort of a limit of those polymorphisms. So what are you going to do is that you have exactly, we have this particular, so you have alpha 1, alpha 2 to alpha sub r are the weights of all the different tuples you have. Yes, yeah, the analysis will always be local. So you have some r1 to ruk, and I want to, and I'll even just say, and I want to prove that the rounded values of u1 through uk will satisfy this relation R. And the way I'll do that is that I will say that the rounded value will be the output of the polymorphism on certain tuples. Okay? So roughly the idea is going to be the following. I'm going to write down tuples. So these are the proportion of tuples. I will write down, roughly speaking, so I'll write down W1. So basically I'll have Wi. So basically write the first tuple W1 times, the second tuple W2 times. So where Wi is almost equal to alpha I times M. So M large, M very large, M large enough. So basically you write this guy W1 times, W2 times, 2WR times. Okay, and then the summation of Wi is going to be M. So that makes sense. And you can also, formally what does this mean? You can make sure that everybody is within one of this. Okay, so this is something you can easily do. Okay, you can give floor of alpha 1 M to this and so on, and then adjust up if needed. And note that summation of alpha I is 1, so this is all. The summation alpha I is 1. So again, basically take many copies of each of these tuples in proportion to the frequencies given by the LP. And now what are you going to do? So now if I apply the majority, note that if I take this variable U1, the proportion of times I am 1 here is going to be very close to the LP value XU. Because if I actually used alpha 1 through alpha M, as if my proportions are exactly alpha 1 through alpha M, then indeed this sum will have exactly XU1 M will be the sum. But of course I'm slightly off, but that shouldn't really matter. Because I'm off by 1 for each I. So if my M is much, much more than the number of tuples in my relation, and note that these are all constants, arity is constant, then this error will be very small. Okay, so what I'm saying is something very simple, which is that the LP gives a distribution whose marginal exactly gives me a percentage of XU1. So let me just discretize this, take a very large M, and take samples according to this distribution, M samples according to this empirical distribution. If you want, you can think of it as sort of a randomized process too. So you line up all those tuples as rows, and then if you apply the majority function, basically when I look at a column, the proportion of 1s will be very close to XU1, or XU for that column. Therefore, what the majority function does will be exactly what my rounding does. Okay, and this is a simple but very nice conceptual link between polymorphisms and rounding algorithms. So again, the proportion of 1s seen by the majority function in each column is very close to the LP value. And therefore, I'll be doing the correct thing. So as long as I'm not very close to 1/2, I'll be fine. So M has to be odd. Yeah, it doesn't. Yeah, that's fine. Yeah. So you just pick M to be anything very big, and then you just have to satisfy all these conditions. So this is something you can do. You can start with alpha I. Take M to be a huge odd number. Take floor of alpha M copies for I. And then basically just increase a few of these things by 1. Note that your deficiency will be less than M, so you have M different things. So am I saying it correct? Yeah. Yeah, something like this. I mean, you just start with something very close to alpha M and just increase some of them by 1 to make up the sum. Yeah.
Last time for Hornset, we cleared denominators by whatever the denominator is.
Right, right.
This time we can't do that because that
Yes.
is an even number.
Right.
That is the only thing to avoid.
Yeah. Yeah. Also, it's important that I mean, there it was, whether you had, I mean, there the polymorphism was and, right? So it was, yeah. So it's a bit different here.
Suppose you had this majority for every arity, not only odd arity.
Yeah.
Then you could clear denominators and not have to do this rounding of alpha A.
That's true, I guess. Yeah. Yeah, but then majority of all even things is not well defined, so you get into some soup there. Right? So
it's enough to have majority M for large enough.
odd arities, yeah.
But does that automatically give you small?
So that then the LP will work.
So how large arity are you using that?
So that should be much more than the size of the largest relation, basically. That's it.
Also the alpha thrown up by the LP.
Yeah.
In bit complexity, it has something to do with the size of
Right, so you just want to make sure that you, if you're, yeah, so, I see. So,
That is why it would be growing. It would not be something which, because the additives of the R's is still a constant.
yeah, yeah.
But,
That's right. So your XU might be something very, very close to 1/2, and you might want to approximate it and not go to the other side. So some of the bit complexity type things will prop up. Yeah. Yeah. But I think those should be manageable because,
yeah, that's fine.
yeah, yeah.
You have all the majority then.
No, but also note one very important thing here is that, okay, I think I should clarify this. This part is only in the analysis, so it really doesn't matter how big M is. So note that this is not algorithmic part. So M can be, even if the complexity, indeed what you said, M will have to sometimes be very big because, it's just the bit complexity of the solution may be polynomial, but the denominator may be exponential or something. So M has to be much bigger than that so that if you're half minus 1/2 to the n, you don't want to cross over half. So M has to be huge. But it doesn't matter because we are just using it in the analysis. And the rounding algorithm itself is just this simple threshold.
No, what I meant was, the way we are using it in the analysis, it's not enough that you have all odd majorities up to a number which is dictated by the relations.
Yes.
Because as your instances increases, you need larger and larger.
Yeah, because of the analysis, because you don't want to, because of this part, yeah. Because you want to approximate the frequencies very, very well. And you have a discretization error of roughly like size of R by M. So this should be much smaller than that, you don't cross over the boundary. Okay, so I'm out of time, but very quickly, so I'll just say, it turns out, so this is a problem because this obviously will not work if I get anything half, the rounding is not even well defined. So what we do is that we want to solve the LP and we want to avoid getting 1/2 solution. There are a couple of ways to handle it. If you get a solution, you can jiggle the solution so that no variable is 1/2. This is something you can do. But a more principled, nicer way is basically just to solve the LP over some other ring than rationals. Okay, so of course you could try to solve the LP over integers, but that's of course NP hard. So what you do is that you solve LP over some ring, let's say square root 2 adjoined with Z. Okay, so this is some ring and it's a dense ring because square root 2 minus 1 is less than 1, so you can power it and make arbitrary small numbers. So for any real number, there is going to be something very close to it in Z root 2. So it's a dense ring, and you solve it over that, and then of course this has no rational numbers other than integers, and therefore this cannot. So this is a valid routing. Okay, so and turns out, why can you solve LPs over this thing? This is something we give an algorithm for, so I won't get into that algorithm. But just to give you a polymorphic teaser, suppose you have two solutions x and y to an LP. Suppose you have mx lesser or equal to b, and you have two solutions, let's say y and z are solutions in z root 2 to the n. Suppose this is an n variable system, and I have two solutions to this linear program. Then I can combine them in a non-trivial way to get a solution, which is I can take square root 2 minus 1 times y plus 2 minus square root 2 times z is also a solution. Because this is just a convex combination, but it's a convex combination where both the numbers lie in the ring Z root 2. Right? And that's why somehow this polymorphic principle should say that, oh, I have a non-trivial way to combine solutions. So for LPs, of course, any convex combination is valid. So there's an abundant way. So it's convex, you solve it. Here, there are ways to combine solutions with coefficients in the ring, which also gives you a solution. So the polymorphic principle should tell you that something non-trivial is going on here. You should be able to find solutions to LPs in these rings. Right, and indeed, if you solve that, then you get a clean theorem that you just try to solve the LP over this, which is something you can do in polynomial time using adaptation of known techniques. This is another thing we work out, and then you get this theorem. Okay, so I think I should stop here. So.